Hello everyone, I hope you all enjoyed the little animation I prepared for you. Tonight, I'll talk a little about the rigs and mechanics I used in order to create the final animation. The animation I made contains several rigs, some complex, some simple. Let's start off with taking a look at the bird rig. The bird contains several attributes that control its flying animation. The wing rotation is controlled by set-driven keys. I attached a cluster to the end of the feathers. The clusters are also animated so it looks like the wings are bending. Perhaps you've noticed a bit of a stretch and squash going on. The stretch and squash is rigged by applying a lattice to the bird's geometry, then linking a cluster to the lattice points. This means when we scale the cluster, the lattice points will move outwards, which will effectively stretch and squash the whole bird. Finally, the cluster scale is connected to an attribute. The wing rotation, the feather bend, and the stretch and squash rig are connected to an attribute called flying animation. Now we can control the entire flying animation with one attribute. In one particular shot, the bird is being grabbed by its legs while flying. To set this up, the feet had to remain stationary, while the rest of the flying animation continued. This was a bit of a challenge because normally the bird's legs were rotating and moving during the flying animation. I tackled this with some node networks. In order to get rid of the vertical movement in the feet, we take the y-coordinate of the main body it's attached to and reverse it. Now in this if statement, there's a new attribute coming in called hanging feet. Here we say, if hanging feet is not true, don't do anything. But if it is true, send the opposite value of the body's y position to the clusters that control the feet. The movements cancel each other out, making it seem like the feet are standing still in mid-air. Now we tackled the up and down movement of the feet, but they are still rotating a bit. So back in Hypershade, we say with another if statement, if hanging feet is true, don't do the set-driven key animation. To round it up, the bird needs a few more things to function in the final animation. I set up a hit squash attribute, once again controlled by a lattice. A pupil size attribute, controlled by a cluster. And a beak open attribute, controlled by a blend shape. Some objects in the animation needed a simple rig to function. The umbrella is a rig to flip inside out. The flipping is done with a simple blend shape connected to an attribute. However, the support sticks are separated and need to move with it. This is done by creating a locator and point-on poly constraining it to the height of where the sticks need to attach. Then I created clusters out of the tip of the sticks and connected the clusters to the locator height. Now the tip clusters will move accordingly when the umbrella flips inside out. The simplest rig is the bicycle. The wheels and pedals can be rotated using an attribute. The pedals are simply point constrained, so they will not rotate. Finally, the bike has a stretch and squash rig. At last, we arrived at the protagonist of our story. I will show you all the ins and outs of his rig. The head is attached to the main body with the use of an IK handle. In addition to its head movement, it can also rotate its eyes for simple expressions. The exhaust pipe is animated using a set-driven key. It will start moving when you raise the attribute's value. In the graph editor, I made sure pre and post infinite cycle was turned on, so the animation is looped. Because my animation has a lot of fast movements, a stretch and squash rig was vital for dynamic animation. The stretch and squash is rigged by applying a lattice to the robot's geometry, then linking a cluster to the lattice points. Finally, the cluster scale is connected to an attribute. The robot has a little compartment where he stores the treasures from all his adventures. He can open and close the door to reveal his hidden limb. The robot arm has by far the most options available. We can hide and unhide his arm when he's done using it. We can extend the stretchy arm, which is controlled by using a spline IK. The control points of the curve are once again linked to clusters, which allows me to control and keyframe the movement of the arm. The hand can be opened and closed too, for some convenient bird grabbing. The wheels of the robot are by far the most complex components. The whole rig is based around the torso controlling everything, with the wheels dangling down, grabbing hold of anything it can reach. The legs of the wheels contain a simple IK handle and a spring that blends between two states depending on the distance stretched. The rotation of the wheels is controlled by an expression script that checks the direction it's pointing at and the direction it moves in, and calculates the amount of rotation as a result. This way, the wheels will never rotate when moving upwards or sideways, but only in its local forward direction. My animation happens to contain a lot of rough terrain for the robot to cross. This requires a good and working suspension system. The wheels are attached to IK handles, which are directly constrained to a controller on the bottom of the wheels, which is then geometry constrained to the ground geometry. With a little translation limiting and magic, the wheels are now snapping to the ground when they get close enough. Let's see what happens when the robot tries to go up a hill. The wheels seem to be clipping through the ground geometry. Placing our geometry constraint on the bottom of the wheel wasn't very effective. In order to fix this, I did some more rigging and came to a solution. I created a separate locator that could only rotate around the circumference of the wheel. Next, I used a very powerful tool called normal constraint. The normal constraint will take the normal direction of the nearest face on the ground and apply it to the locator. Because the geometry constraint locator is parented to the normal constraint locator and is only limited to the Y translation, it can now accurately predict where the wheel is going to hit the ground first and push back the wheels accordingly. Because the robot is covering a lot of terrain in animation, a lot of polys are needed in order to build all the terrain zooming by. This would be both unpractical and unoptimized. Fortunately, there's a workaround. I generated a cylinder in Houdini that has a path and rocks covering the entire surface. Within Maya, I applied a lattice deformer to the cylinder and shaped it into the flat shape I want. Now when we rotate the cylinder itself, it will be restricted and kept inside the lattice point, giving a conveyor belt effect. Now using a point on poly constraint, we can select a vertex and constrain a prop to it. Now when the conveyor belt is rotating and deforming, the props will retain their original shape. The Viewport 2.0 renderer has a very limited shadow quality that drops when the amount of visible polygons increase. To achieve the highest possible shadow quality, we have to limit the amount of polygons in the scene to the bare minimum. Here you're seeing a short time lapse of the animation being played from a bird's eye view. You can see the robot teleporting to new locations in between shots and enabling and disabling terrain depending on the shot. Thank you for watching. I hope this rigging video was informative. Have a nice evening and good night.